Welcome back. In this final session, we are going to talk about feature selection and reduction of dimensionality. So let's start by understanding the key problem in a high dimensional data, something known as curse of dimensionality. This refers to the fact that as we add more features to a data set, instead of getting better performance, model can actually perform worse. And here is why. First, look at the section on data sparsity. In low dimensions, data points are packed relatively close to each other, making it easier for model to learn pattern. But in high dimension, the space becomes vast and data points spread out like a distant stars in galaxy. This sparsity makes it difficult for model to detect meaningful clusters or trends. Second, we see a distance breakdown. Many machine learning models like KNN or clustering algorithms rely on distance calculation. But in high dimension, the difference between the nearest and the farthest neighbor becomes negligible. So all distance start to look the same. This renders those models ineffective. And third, there is a overfitting risk. With too many features, especially if we have a limited samples, model can start learning noise rather than actual signal. They memorize instead of generalize, and that's a recipe for a poor real world performance. And finally, we have a resource explosion. Every new feature we add increase the computational and memory requirement, sometimes exponentially. This slows down training, bloats our models, and raise our cost. So even if you're adding 10 or 20 irrelevant features which sound harmless, can severely degrade the model performance. That's why the curse of dimensionality is such a fundamental problem and why we need feature reduction techniques, which we are going to explore in the coming slides. So as we begin with working with a data set that contains a large number of features like our own data set, like which with 96 features, it's important to understand that more isn't always better. Okay, so here we try to see what is a problem of high dimension data. So you see in the diagram that you see a chaotic network. That's what the feature space looks like, where it's bloated with very irrelevant or low variance features. On the right, we have, on the same diagram, if you see that when we perform the feature reduction, and now the network is much more organized, focused, and easy to learn. So high dimensional data can hurt your model, more than it helps. It increases the risk of overfitting. Your model may memorize noise instead of learning signals. It makes training slower and less efficient. So many features are often correlated or uninformative, adding clutter, and from a practical standpoint, the model becomes harder to interpret, which matters when you need to explain results to stakeholders. So feature reduction is not just a cleanup step, it is a strategic necessity when working with a data set like what we are dealing right now. So it helps us to focus on what matters, improve performance, and build smart models. Now we discussed about reducing features, right? What is the challenges having a lot number of features. Now let's talk about what is feature reduction actually mean. Broadly, there are two main approaches. One is feature selection and feature extraction. And they sound similar, but they serve very different purpose. So we see that on feature selection, this means picking the most important features from your original data set. You keep features like, for example, like ROA or debt ratio because they have been statistically proven to be predictive. It is very transparent and explainable, great for model where stakeholder want to know why a prediction was made. Basically, I want to know, for example, if a customer has churned, I want to know what features has contributed for this churn. If I know that a company is going bankrupt, I want to know like what features actually contributed to this prediction of a company going bankrupt. On another hand, we have feature extraction. This is more about compression. Instead of picking individual columns, we combine feature using a math and like something like a PCA, okay, to create new synthetic ones. These features are great for modeling, but hard to interpret because they don't directly represent anything you collected. So the big trade-off is whether Either you want to interpret your results or explainability versus compression. If you want to explain why the model made a specific prediction, you should go for a feature selection where you select only the features you want. But if you don't have the requirement, but you want to reduce the features, you want to derive some features, then you can go for a feature extraction. So another aspect is that if you focus, if you want focus purely on the predictive power and performance, then in that case also feature extraction might make sense for you. So now that we have established why feature reduction is valuable and when to use it, let's walk through step-by-step process. In step 1, we remove the low variance features. So we start by eliminating features that barely changes across samples. They don't offer any useful signals. They are just taking up space and slowing the model down. In step 2, we drop highly correlated features. Many features in finance or ratio-based data are mathematically or logically correlated. So we drop one feature from each pair with a correlation above 0.9 to prevent any multicollinearity. Next, we use univariate feature selection. So we can use statistical tests like ANOVA to evaluate each feature predictive power in isolation. I'm going to talk about what is ANOVA in the coming slides. So this gives us a quick ranking, a short list of potentially strong features. Then in step 4, we use model-based selection. Here we let the model help us, like algorithm like a random forest or XGBoost will evaluate which features are actually help in making prediction and assign important score. So now let's go in details of each step. Our step number 1 is removing low variance features. So what does this mean? A feature with little variation across rows. For example, if almost every company in your data set has a license, doesn't add any useful signal to your model. It's almost same value for everyone. So it won't help making predictions. So in table below, you can see that we have calculated the variance of 3 features. Has license as a variance of 0.001. So almost no variation. So we drop it. So default flag is even worse with 0.005, again dropped. But ROA, return on assets, has a healthy variance of 0.21. So we keep that. So we typically use a threshold like 0.01. Anything below that gets removed, and we can automate this step by using variant threshold from, like, if you are using any scikit-learn library, we have some functions, we can use that one idea. So what is the main idea is feature that doesn't change much across the data set don't contribute to learning pattern, and keeping them just add noise and complexity. So basically, just summarize, right? If you're having some 30 features and all these 30 features are same across every row, every data point, model doesn't have anything to learn from these features. They are just improving the model complexity or maybe increasing the computational power. So better to drop them instead of keeping them. So this step helps clean up our data and make your model more efficient. So by end of step 1, we have removed all the low variance features. Now we need to focus on dropping highly correlated features. Sometimes in our data set, 2 features are basically saying same thing, just in different word. So this is a problem because it introduces duplicity, can lead to multicollinearity, and may confuse our overfit model. So look at the first row in the table. Debt ratio and liability to assets have a correlation of 0.96, meaning they move almost perfectly together. In this case, we drop one of them to avoid a duplicate information. In contrast, in second pair, the operating profit margin and gross margin have a correlation of 0.88. That's high, but still below the common threshold of 0.9. So we keep both of them. So we follow a simple process here. Calculate correlation matrix and look for feature pairs with correlation greater than 0.9. Then we select a representative from each group, the one with the better domain relevance or predictive power. So then we preserve information while reducing the redundancy. So this step helps simplify the model and reduce the noise. Just like cleaning up duplicates in a spreadsheet, before you do analysis. So after removing low variance features and handling highly correlated ones, our next step is univariate feature selections. This approach is all about testing each feature individually to see how strong it relates to target variables. Let's walk through the key points. Individual testing. Each feature is tested on its own, one at a time, using a statistical method. This means we look up at the direct relationship with the target variable without considering other features. Then predictive power ranking. Based on the test, we rank the feature. The idea is simple. The more predictive a feature is on its own, the higher it ranks. This gives us a very way to prioritize which feature to keep and which one to drop. Then we use different tests depending upon the type of data. So for example, if you're having a categorical features, we can use chi-square test. For numerical features, we typically use ANOVA F-test or correlation based methods. So, but there is some important, considerations here. One is that univariate selection doesn't capture interactions between features. So it ignores a combination that might be powerful together but weak individually. So while it's fast and useful, we need to be careful not relying on it alone. So this step often used in early stages of feature reduction, especially in a high dimensional data set, to quickly narrow down the most promising features. Now let's take a moment to understand ANOVA F-score, which is very commonly used in univariate feature selection, especially when the target variables is a categorical. So what is ANOVA F-score, right? The F-score comes from ANOVA or analysis of variance. It helps us measure how well features can differentiate between classes. For example, bankrupt versus non-bankrupt companies. The formula is very simple. Variance between the groups divided by the variance within the groups. So the numerator captures how much group means differ. The denominator captures the spread within the each group. So for example, take one example where you have to test how is the impact on sleep for a different drinks. For example, you have a coffee, you have a tea, and say you have water. Now you can test 10 people consuming coffee, 10 people consuming tea, 10 people consuming water. Now you see how much time they take to sleep after that, right? Your reaction time. So there is a variance among the group, within the group, like, one person might take quickly within an hour. Some people might take delay the sleep by 2 hours. For some people, 3 hours. In each group is different. We see the variance within the group, right? For the coffee group, for the tea group, for the water group. Then we see the variance across the groups, like whether is there a difference between the people who drinking coffee versus people drinking water, right? So a higher F score means that feature does better job at separating the classes, which is exactly what we want for a classification task. Say, take the example of our data set. Let's say we are using ROA as a feature, right? We are having ROA as a feature. Bankrupt companies have an average ROA of, say, minus 15%, but non-bankrupt companies are having average ROI of 10%. That's a big difference, and it leads to higher F score because the variance between two groups is large compared to the variance within each group. So the F score tells us that ROA is a strong discriminator between the financial outcomes. So next, feature selection application. Here where it becomes actionable. So in univariate selection, we calculate F score for all features and keep the one with the highest values. This is different from correlation, which assumes a linear relationship and doesn't work well with the categorical outcomes. So F score is ideal when the target classification label like bankrupt or non-bankrupt. So when building model, this helps us to quickly identify which feature have that most predictive power and one at a time. In the previous session, we discussed about the chi-square test. Now we discussed about ANOVA test. Let's see which one to use when. So when doing univariate feature selection, one of the most important decision is choosing the right statistical test, and that depends entirely on type of the features and target variables. Let's break down when to use a chi-square test versus ANOVA F test. Chi-square test. Use this when both your feature and target are categorical. It measures whether there is a dependency or association between two categorical variables. For example, if you are checking if gender affects loan approval, we use chi-square test. It is great for binary flags like has license, encoded category like regions or sectors. ANOVA after this is used when features is a numerical and the target is a categorical. It checks whether the mean difference slides significantly across the categories. So for example, if you're testing whether ROA, return on assets, differs between the bankrupt and non-bankrupt company, that's where ANOVA shines. So it is perfect for financial ratios, percentages or other continuous features. So in our case, where we are trying to predict the company will go bankrupt or not, most of the features are numerical like ROA, gross margin, and our target is binary categorical, bankrupts versus non-bankrupt. So the ANOVA F test is the right choice for selecting which features are most predictive. By matching the test to the data type, we ensure our feature selection is both statistically valid and practically meaningful. So up until now, we looked at feature-based method like chi-square and ANOVA F-score for selecting features. They are fast and simple, but they come with major limitations. They evaluate each feature independently, and that means they often miss the big picture. So there are basic statistical tests. They work well when you want quick filtering, you have a clear idea what to expect from each feature, but the problem is they can't detect feature interactions. So that example, two weak features might be powerful together. They miss non-linear relationship. So if a data set is complex, filter method might oversimplify the story. So next one is the model based approach. This is where we let the machine learning model themselves help us decide what's important. It can capture complex pattern including non-linear relationship. It identifies interaction that manual or univariate methods might miss. And it is tailored for the actual algorithm you plan to use. For example, a random forest or XGBoost can rank features based on how much they reduce error. So you should consider model-based selection when you have a large number of features, say 20 or more, you suspect feature interaction, you filter method don't improve performance, or you have already planning to use a tree-based model like a random forest or gradient boost trees. So to summarize, use filter method for fast early stage filtering, use model-based selection when accuracy matters and the relationships are complex. So once we move beyond filter based methods, a powerful way to select feature is used a machine learning model itself like XGBoost to tell us what matters most. So here we are, so at the top, if you see in this below diagram at the top, the return on assets is far by the most influential feature in predicting the bankruptcy. Next come debt ratio, then cash flow and working capital. But if you see go down, something like inventory turnover or asset turnover have minimal importance and might be candidate for removal. So these scores come from the model internal decision trees. They reflect how often and how effectively each feature is used to split the data and reduce the prediction error. So why is XGBoost for feature ranking? It gracefully deals with the missing values and captures non-linear relationship right out of the box, and then it can access access ranking easily. So once a model is trained, you can access these scores using any of the methods in within the the model easily. And unlike statistical method like ANOVA or chi-square, XGBoost detect interactions between features, something that matters a lot in complex financial data sets like what we have. So instead of relying on statistical tests, we now let the model tell us what it needs more. This is especially useful when we are dealing with 20 plus features and can't afford to guess. In addition to XGBoost, another excellent tool for model feature selection is random forest algorithm. So let's first see what is random forest is powerful option, especially for noisy or high dimensional data set. So random forest builds many decision trees, each trained on a different subset of the same data. So it then averages the results, which makes the final feature importance scores more stable and less sensitive to noise compared to individual decision trees. So the algorithm evaluates feature importance by measuring the average decrease in Gini impurity. That is how much each feature helps split the data into pure groups. The more feature reduces impurity across the trees, the higher its importance score. And then another thing is that one of the key benefits of random forest is robustness to noise. If your dataset has many variables and if you suspect your features have a weak signals, random forest often gives more consistent results than XGBoost. So random forest and XGBoost don't always agree. That sometimes is okay. In practice, we can use both to cross-validate feature importance from multiple perspectives. So there is another technique which we can use for feature reduction workflow, which is a PCA or principal component analysis. So PCA is a powerful technique for reducing number of features when you have a many correlated numerical variables. So what PCA does? PCA transforms your original features into fewer synthetic variables called principal components. For example, it can take 96 original features and reduce them into 10 to 20 components that captures most of the information. These components are uncorrelated and are formed by combining original features in a linear way. The goal is to retain the most variance, the most signal while removing the noise. So when to use PCA? PCA is especially useful when your dataset has got many correlated numeric features and then your model, you are using a model that are very sensitive to multi-collinearity like logistic regression or KNN. You need to improve computational efficiency, like fewer features means faster training and less overfitting. But one thing keep in mind, PCA transforms your features into components. So you lose their explainability. So if you want to explain why the model made a particular select prediction, you will not be able to do with the PCA. So it reduces the complexity and speed of the computation, but it sacrifices the explainability. So you can't point, say the model predicted that this is a this transaction is a fraud because of these features, right? That you cannot do. But it works best when features are standardized. So scaling is important before applying PCA. So to summarize, if you are prioritizing predictive performance and efficiency over explainability, PCA can dramatically simplify your model while keeping the signal strong. So now let's head back to our Jupyter notebook and start working on the reducing the features. So as usual, we'll import our library here. Now you can see that I'm taking the balanced data set which we did in the previous session. So we started with the removing outliers that we fed into the smart which actually did a class, reduced the class imbalance and made a balanced data set. Now we are taking the same data set and then trying to we are doing the feature reduction there. So let's see, first look in this data. So now they are having the total 95 features are there. So before we reduce the features, we are seeing that we are having this many features, right? Now we can see that we are having equally balanced classes now, both bankrupt and non-bankrupt. We are having equal number of values. Now let's see what we'll do. We'll do 4 steps: step 1, step 2, step 3, step 4. Each step we will try to reduce. First we'll start looking at the covariance, then we do ANOVA test, then we'll do a model based selection. So we'll go step by step. So we are just trying to capture that information here. So the target shape. Now the first step 1, we want to remove the low variance features. So we need to compute the variance among the features, and any feature with the less than 0.01 we are going to remove them. Apart from that, we are also measuring the coefficient of variation. So what is coefficient of variation? It measures the relative variability of a single variable. It tells how large the standard deviation is in relation to the mean, right? So for example, if you are comparing, say in the medical, okay, blood pressure versus heart rate, or comparing risk across different investments. So what I mean is that it is used to compare the variability between the data set, the different units or means. Now let's see what we're doing here. We are trying to find the variance threshold 0.01. So we're trying to get the feature variance or low variance features, and then we are trying to see whether the coefficient of variation less than 0.1. So we are also trying to plot the this distribution of feature variance in this data set. So let's run this. Now you can see that so the mean variance is this, median, mean variance, max variance. So now we can see that features less than 0.01, that means they don't really contribute to the model to learn something. Such a low variance is there. So how many variables are there like that? You can see that almost 82 features. That means such a huge data set you're having. That means we are having a lot of features which doesn't add any value to the model training. That's what it means. That means so we need maybe features to be removed is 82 features to be removed, right? So now we can see the distribution of feature variance here. Now in the step 1 we looked into all the variances of all the features. I think we pretty much removed most of the features. So what are the features remaining right now should be the features we should be good with. Now we'll continue our analysis further. Let's see in step 2 we drop highly correlated features. So for that we first need to find the correlation matrix, and then we have a threshold of 0.9. So anything less than 0.9 is what we are going to drop. Now we can see that as of now we are having only 13 features. So we didn't remove any features because distribution of features correlation before and after is there. So we are not removing any features because we didn't find any features with a correlation greater than 0.9. Next we will do ANOVA F test for on the remaining features. Now let's see, in the ANOVA test we are having the important thing is that in top 10 features we'll find F score, the p value, and then the features p value less than 0.05, 0.01, 0.001. So we'll try to find all of them and see like which features to remove, which features to drop. So now let's walk through this what output. So top 10 features F score, we have this F score and we have the p value. So features p value less than 0.05 is 11, but 11 I think 0.01 is there. So pretty much in this also we have all the features which are required. We are not removing any features in this stage also, right? Next we are going to the step 4 we discuss model based features. So we'll use two models, random forest and XGBoost, to see like which features can be of more importance, and we plot them. So now we can see that I'm using all scikit-learn random forest classifier with estimator 100. So and then we are also using XGBoost model here. So now we can see that random forest feature important. These are the features which are important as per random forest, and XGBoost is giving this feature importance. Pretty much more or less both of them are agreeing on the same set of features, but the rank might be slightly different. Each will rank differently. So you take combined feature ranking from the top 15. These are all the top features selected, like these are all 13 features we selected, and then their ranking. So now let's summarize the feature reduction what we are having. So this is what the original feature what we are having, around 95 features. Then step 1, step 2, step 3. See, we did first variance. I think we eliminate a lot of features. Step 1 itself, and step 2, step 3, step 4. What did we just only confirmed whether we did the right thing or not, right? So that means then once we done with everything, we'll go ahead and then export this features. Some small genetic fixed error, small error is there maybe due to the path issue, but the feature it summarized all the features, it removed everything. I just need to save this in a CSV file. Now what happens, now I am having a final data set. I might start training my model on this data set in the next step.